Okay, so I'm going to start with the problem that we already solved multiple times. Now, here is the problem that I want to set up. What we have is we have the first revolute joint. On top of it, there is this second revolute joint. And then you have an end effector. So this is the end effector. This is the first revolute joint. This is the second revolute joint. So I have a robot which is R parallel R. And I'm gonna give you the lengths. This is L1, this is L2. If we follow the convention, this is going to be my Z0 axis. This is going to be my X0 axis. And this is going to be my Y0 axis. Same thing. This is going to be my Z1 axis. This is going to be my X1 axis. And this is going to be my Y1 axis. Last but not least, this is going to be my Z2 axis. This is going to be my X2 axis. And this is going to be my Y2 axis. I want to draw the top view of this robot. So if I draw the top view, what I'm going to see is I'm going to see X0 and I'm going to see Y0. Right now, the kinematic diagram that I have drawn is at 0 angles. But assuming that your theta 1, this is your theta 1, and your theta 2, they are non-zero angles, then your kinematic diagram would look something like this. And we have worked out this problem previously. This is L1, this is L2, this is your first revolute joint, this is your second revolute joint. This angle is theta 1. This angle is theta 2. And if I were to draw the total angle between the second link and the X0 axis, the total angle is going to be theta 1 plus theta 2. If I look at the horizontal intercept, and this is something not new that you already know, this is going to be L1 cosine theta 1. This distance is going to be L2 cosine theta 1 plus theta 2. Now, and if you look at the intercept on the y-axis, this is going to be L1 sine theta 1. And this distance is going to be L2 sine theta 1 plus theta 2. Are you with me? So if I were to write the end effector position, so end effector position will always be written in terms of inertial or the zeroth coordinate frame, which means the end effector position will be expressed with respect to X0, Y0, and Z0. So I'm going to write this down here. I'm going to call this A1 and I'm going to call this A2. This is A1 and A2. So the end effector position Px will be given as L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. Py is given as L1 sine theta 1 plus L2 sine theta 1 plus theta 2. And last but not least, Pz, which is the end effector position about Z0, is going to be A1 plus A2. and I did not do any rotation matrices. But even if you do rotation matrices, you are gonna get the exact same answer. Everyone understood? Px, Py, Pz. Now what I'm gonna do here is I want to find out the velocity of the end effector, which means how fast or how slow the end effector is moving. The easiest way to find the velocity is take the derivative of the position. Do you agree with me? So what I'm gonna do is I'm gonna take the derivative of the position. But I want you to understand the derivative is going to be with respect to time. Please note L1 and L2, they are constant. Theta 1 and theta 2 are also dependent on time. What it means is when I take the derivative, I will have to use UV rule. Let me repeat this once again. So a side note. Side note is, imagine if you have U is equal to A sine theta 1, okay, where U is the function of t, A is a constant, A is equal to constant, and theta 1 is also function of time. Then if I take the derivative, du by dt is equal to A comes out, and then I have d by dt of sine theta 1. And here, since theta 1 is dependent on time, the answer is going to be A, derivative of sine, which is cosine theta 1 plus derivative of theta 1 with respect to time. So the answer to this derivative is going to be A cosine theta 1 multiplied by theta 1 dot. Everyone understood this? And the reason for that is, even though L is a constant, theta 1 is dependent on time, and sine is the function that is dependent on theta 1. So now when I'm going to take the derivative, this small expression is going to expand. So I will start taking the derivatives. So px d by dt of px is equal to px dot. L1 is a constant, so L1 comes out of it. The derivative of cosine theta is minus sine theta 1. Derivative of theta 1 is theta 1 dot. Are you with me? Next step, I have L2. L2 is a constant that comes out. I have cosine theta 1 plus theta 2. So what I need to do is I need to take the derivative of minus sine theta 1 plus theta 2. And then what I need to do is I need to take the derivative of these two. So I will have theta 1 dot plus theta 2 dot. Are you with me so far? Now, if I want to expand this further, I would say L1 sine theta 1 dot, this guy plus L2, this is going to have minus sine theta 1 plus theta 2 theta 1 dot minus L2 sine theta 1 plus theta 2 theta 2 dot. So this expression is going to look like this. Now I have theta 1 dot here. I have theta 1 dot here. So I can combine these two together, and my answer is going to be L1 sine theta 1 minus L2 sine theta 1 plus theta 2 theta 1 dot minus L2 sine theta 1 plus theta 2 dot. So I have an expression for Px dot as this big expression, L1 sine theta 1 minus L2 sine theta 1 plus theta 2, the whole thing multiplied by the theta 1 dot minus L2 sine theta 1 plus theta 2 and theta 2 dot. Everyone understood this? I have to repeat the exact same process for Py. D by dt of Py is equal to Py dot, and that is going to be L1 sine theta becomes cosine theta, theta 1 dot, plus L2 sine theta 1 plus theta 2 becomes cosine theta 1 plus theta 2 multiplied by the derivative of theta 1 plus theta 2, which is theta 1 dot plus theta 2 dot, which means I will have to expand this and collect the terms, and I'm going to take a shortcut here real quick. This is going to look like Py dot is equal to L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2 theta 1 dot plus L2 cosine theta 1 plus theta 2 dot. Now last, if you look at Pz, Pz is A1 plus A2. So if I take the derivative of Pz, that is going to be 0. So Pz dot, and I'm going to write this down. And just to be very clear, this will be 0 theta 1 dot plus 0 theta 2 dot. Are you with me? So I want you to focus on these three equations: equation 1, equation 2, and equation 3. And what I want to do is, I want to take these three equations and put them in a vector matrix notation. Before I go any further, understand what I have done is I have found out the end effector position in the inertial or the zeroth coordinate. I took the derivative, and when I took the derivative, I used the UV rule, and I have now three equations: Px dot, Py dot, and Pz dot, and I want to write these three equations in matrix form. Matrix forms means I have to write this equation like Px dot, Py dot, and Pz dot. And I'm gonna have this matrix. Actually, I will need a bigger matrix. I'm gonna have this matrix, and I'm gonna have theta 1 dot and theta 2 dot. So I want to write this in a matrix form, and see this matrix comes out very nicely as minus L1 sine theta 1 minus L2 sine theta 1 plus theta 2 minus L2 sine theta 1 plus theta 2. Then I get L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2 and L2 cosine theta 1 plus theta 2. And clearly Pz dot is a 0. So there will be 0 here and 0 here. Everyone understood this? This matrix is called as the Jacobian. This matrix is called as the Jacobian. Everyone understood this? So what is a Jacobian? In terms of robotics, Jacobian gives you the relationship between the end effector velocity and the joint velocities. So theta 1 dot and theta 2 dot are the rate at which theta 1 and theta 2 are changing, how fast those joints are moving. And once I multiply with that matrix, I get the end effector velocities. Everyone understood this? This is what is the meaning of Jacobian. Now I want to give you one more interpretation of Jacobian. So one more interpretation of Jacobian is, now what I'm going to do is, I'm going to go with the basic form of derivative. So if you have a function y is equal to f of x, if you want to find out the change in the y, so what you do is, if you want to find out the change in the y, so see, if you have a function which is something like this, so this is y, this is x, and this is f of x. You have y, f, x, and this is f of x. So what does this mean? Which means when x is equal to say 1, you have certain value of y. When x is equal to 2, you have certain value of y. Now, if I want to find out what is the value at point 2, given the value at point 1, I can write this as something like, I can have a straight line approximation between point 1 and point 2. I can say y2 is nothing but y1 plus df by dx multiplied by delta x. So if this change is delta x, the final output is the initial value. This is the slope, and this is the change in the x. Change in x. Everyone with me so far? As long as my point 1 and point 2 are very close to each other, this approach is valid. Everyone agrees with this? So if I want to, and the next step is extremely important. So next step, what I'm trying to do is, I'm saying y2 minus y1 is equal to df by dx multiplied by delta x. In other words, delta y is equal to df by dx multiplied by delta x. So this is the slope or the derivative of the function multiplied by the x difference that gives you the y difference. Everyone understood this? Now please note that this function f of x, there is only one independent variable. This is the independent variable, and this is the dependent variable. So that's why when I take a derivative, it is the complete derivative. Now I want you to visualize a slightly different case. Instead of a curve, I have a surface. Now what do I mean by that? Is I have a function which is z, I have x, and I have y. Actually, I didn't draw it the right angle way. So let me draw it something like this. I have y. And what I have is, rather than a curve, I have a surface. Instead of a curve, I have a surface. And on this surface, what I'm going to do is, I'm going to draw lines which are parallel to y. And I'm going to draw the lines which are parallel to x. Now, this function z is equal to function of x comma y. Do you agree with me? Z is the function of x comma y. Now, I want to answer this very, very important question. How much of change in z is contributed by change in x, and how much of change in z is contributed by the change in y? So let me pose this question slightly differently. Imagine you have $100 and 25 cents. You have $100 and 25 cents. If I give you $10, you would have $110 and 25 cents. If I give you 10 cents, if I just give you 10 cents, then you are going to have $100 and 35 cents. Do you agree with me? So same question I'm trying to ask here, that if the value of z is changed, how much of change is dependent on change in x, and how much of change is dependent on change in y? You clearly agree with me, even though the unit is 10, but in one case I'm adding $10, in other case I'm adding 10 cents. So which means the contribution of change in the x and contribution of change in the y is dependent on relative position in the overall function. What it means, and this is extremely important, if I am interested in finding out change in the z, I need to find out, and this is exactly what you are doing, is partial f x y with respect to partial x multiplied by change in the x plus partial f with partial y multiplied by change in the y. Now, what does this mean? It means this guy is nothing but, if you were to convert the dollars to cents, this contributes to 100 and this is contributing to 1. Does it make sense? So total change in the z is nothing but partial derivative of this function with respect to x multiplied by the change in the x plus partial derivative of this function with respect to y and change in the y. So this is similar to the slope, but this slope is with respect to x. This is also slope, but this slope is slope with respect to y and multiplied by the change in the x and change in the y. What it means is, if you are looking for change in the z, if you are going from one point to the other point, you need to find out how much is the slope in x multiplied by the change in the x. So that is your linear approximation. And then find the slope in the direction of y multiplied by the change in y. That is your linear approximation in y. That will get you to the final point. Everyone understood this? So if you look at that example, this slope with respect to x, which means slope with respect to x is 100 and slope with respect to y is actually 1 for the dollars and cents example. Now I want you to look at the definition of Jacobian. This is extremely important. So px dot is change in the p with respect to time. Change in the p with respect to time. The first guy is change in px with respect to theta 1. Second guy is change in px with respect to theta 2. Second guy is change in py with respect to theta 1 and change in py with respect to theta 2. So in other words, yeah. Yes. And for practical purposes, we are going to use a finite approximation. So our changes are going to be small. So what I want you to understand is if I were to write down the definition of Jacobian, px dot, py dot, pz dot, these are the end effector velocities. Please don't talk. You too. So this will be given as partial px divided by partial theta 1, partial px with respect to partial theta 2. This is partial px with respect to partial theta 1, this is partial py with respect to partial theta 1, and the last one is partial pz with respect to partial theta 1, partial pz with respect to partial theta 2. And this is the real definition of Jacobian, theta 1 and theta 2 dot. And it's very easy to remember. Note, the change is in the quantity of px. So here you have px, here you have py. When you multiply, the first row, first column gets multiplied with theta 1 dot. So that's why px divided by theta 1. First row, second column gets multiplied by theta 2 dot. So in the denominator, you have theta 2. You have py dot. So py divided by partial theta 1, py divided by partial theta 2, pz divided by partial theta 1, pz divided by partial theta 2. Everyone understood this? What it means is I can, rather than taking the derivative, the way I have taken this, I can just write the expression px and py. So I can just take this expression and I can write the expression for derivative pz as partial px by theta 1, partial px by theta 2, partial py by theta 1, partial py by theta 2, and partial pz by theta 1 and partial pz by theta 2. And then I will have theta 1 dot and theta 2 dot. Everyone understood this? This is the Jacobian. Jacobian is nothing but extension of derivative in two or more dimensions. Since in this case, please understand, px is the dependent variable. Px depends upon theta 1, theta 2. So there are two independent variables along with time. And those two independent variables, theta 1 and theta 2, also depend upon time. So what we have that Jacobian. Everyone understood this? So concept of Jacobian is extremely important. So if somebody asks you what is a Jacobian, Jacobian in terms of it's nothing but the extension of derivative when you have two or more independent variables. That's why you have partial. In the case of robotics, Jacobian relates the end effector velocities to the joint velocities. So given the joint velocities, you can find out the end effector velocities. One thing I want you to understand, that this Jacobian is going to change at every theta. Because understand that matrix, as theta 1 is different, as theta 2 is different, every theta 1, every theta 2, that Jacobian value is going to be different. Everyone understood this? Okay. Now what I'm going to do is, I'm going to try to solve this problem wherein I have this robot. I have this robot. Yeah. No, we can move the end effector with uniform velocity. Yeah, so what you need to do is you need to make sure that the product remains constant. So, and as long as that is constant, you can move the end effector at a constant velocity. And that happens all the time. So for an example, if you are doing a coordinated turn, or even if you are doing 3D printing, you are moving, or even for that matter, if you have a paint robot application where the end effector needs to move in a constant velocity, you can make it move in constant velocity. So you need to simultaneously control theta dot, and you have to control theta. So, okay. So what I'm going to do is, I am going to take the same example, but I will try to solve this example from forces point of view. So imagine that we have this two-link robot. Same two-link robots. So we have this two-link robot. This distance is L1. This distance is L2. This distance is L1. This distance is L2. And I'm going to assume that these two links are massless. So L1 and L2 are massless. But at the end, what I have is I have maybe a force in y direction, and I have a force in the x direction. So what this assumption means is you have a robot. That robot is supporting the load at the end effector, but that magnitude of that load is significantly more than the self weight of the links. So you have to make sure that the links themselves do not have significant mass, but the load on this end effector is significant. So what I'm going to do is I'm going to set up the exact same problem. So this is theta 1. And what I have here is I have theta 2, which is theta 1 plus theta 2. So if you look at this problem and the problem that we solved, they're exactly the same. But in this problem, what I was interested in finding out the end effector position and end effector velocity. But in this problem, what I'm interested in is I want to find out what are the torques at this joint. I'm going to call this tau 1. I'm going to call this tau 1, and I'm going to call this tau 2. So here is the problem. So and these two problems are extremely important. In the first problem, I wanted to find out what was the velocity of the end effector and how is that velocity of the end effector related to the joint velocity. In this problem, what I want to do is I'm looking at a static force problem, which means my robot is not moving. But on that robot, there is an upward force and there is a downward, actually there is a downward force and there is a sideways force. So there is f of y and there is f of x. And how much of torque I need to supply at these joints so that I can support that end effector load. Everyone understood this? In the previous problem, I was interested in the motion, the movement. So I wanted to find out how do I relate the joint velocities with the end effector velocities. Here I want to find out what are the joint torques so that the end effector weight is supported. Everyone understood this? Do you guys agree with me? If there is no torque 1 or torque 2, that robot would just fall down. Which means for that robot to maintain that theta 1 and theta 1 plus theta 2, I need to supply some torques tau 1 and tau 2. Everyone understood this? How do I solve this problem? This is called as the static force analysis because the robot is not moving. And this problem sets the stage for the next few chapters where the robot is going to move. So please understand, this robot is in the static position and I want to find out what is the value of tau 1 and tau 2 so that the force Fx and Fy are cancelled. Everyone understood this? Now, just to give you a practical understanding, why is this problem important?
Yes, it's the amount of force closing the links in that question before. Okay, that's why I wanted to explain it a bit further.
Understand, on the end effector, you have forces. If you do vertical arrows and horizontal arrows, those are forces. We don't have any force acting here, or we don't have any force acting here. What we have is the torque at the joint. So the question here is, how much of torque, which is force times the radius, this is a motor. Motor cannot give you force, it's a rotary joint. So how much of torque this motor can give, how much of torque that motor can give, so that collectively tau 1 and tau 2 can support the load Fy and Fx. Everyone understood this? This is a very important problem in robotics. And why this problem is important? Because if you want to program the robot, you always start robot at a very slow speed, 5% or 1%. When you start the robot at a very slow speed, you are nothing but having the quasi-static assumption. What you are assuming is that robot is gradually going very, very slowly changing the position from point A to point B. So indirectly, you are solving static force problem over multiple time steps. Once your static force problem is solved, and once you know that robot is capable of sustaining those static forces, then you increase the speed and then you add inertia effects. Okay, and we'll work on that. But now, how would you solve this problem? This goes back to the basic statics. Summation of forces in x direction is equal to 0. Summation of forces in the y direction is equal to 0. Summation of forces in z direction is equal to 0. Summation of moments about x is equal to 0. Summation of moment about y is equal to 0. And summation of moment about z is equal to 0. In this problem, this is sort of the two-dimensional problem. So which means what I have is I have x and y. So I have x and y. So I'm going to look at forces in the x and y direction is equal to 0 and movement in the z direction is equal to 0. So I'm going to use these conditions of static to solve this problem. Everyone understood this? So what we need to do? For this, we need to draw something called as the free body diagram. What is the free body diagram? Understand, this link is connected to this joint. This joint is connected to the ground. This link is connected to that joint. That joint is connected to the other link. To draw the free body diagram, I'm going to free the bodies, which means all the joint constraints will be removed. So as soon as the joint constraints are removed, internal forces come in the picture. What are the internal forces? Internal forces are the imaginary forces that come into existence as soon as you free the joint. So what's gonna happen is I'm gonna draw the internal forces for this link, and then I'm gonna draw internal forces for this link. So check this out. So we are gonna start with this link. You are gonna have f of y here. You are gonna have f of x here. This, as soon as I free the joint from the hinge, I would have the reaction forces, and these reaction forces are gonna be, I'm gonna call this joint B here. I'm gonna call this joint A here. This will be Bx. This will be By. And clearly here there is tau 2. So I'm gonna draw this tau 2. And this distance is L2. This distance is L2. And this theta is theta 1 plus theta 2. Theta 1 plus theta 2. And I'm going to apply summation of forces in the x direction is equal to 0. In x direction, for my coordinate reference, this is my positive x, this is my positive y. So as you can see here, I have b of x, so plus b of x minus f of x is equal to 0. So that gives me b of x is equal to f of x. Are you with me? Look at, that is the free body diagram. In the free body diagram, since I freed the hinge, the forces, reaction forces, Bx and By came into existence. And when I apply summation of forces in the y direction is equal to 0, I have plus b of y, so plus b of y minus f of y is equal to 0. So I get b of y is equal to f of y. Now I need to find out summation of moment is equal to 0. So I'm gonna take the moment about point B. Summation of moment at point B is equal to 0. Now if I take the moment by f of y, this distance is L2. So this distance is L2 cosine theta 1 plus theta 2. This distance is going to be L2 sine theta 1 plus theta 2. Are you with me so far? So this distance, this horizontal distance, is the link length is L2. So look at the triangle. So L2 cosine theta 1 plus theta 2 is this adjacent, and L2 sine theta 2 plus theta 1 is the opposite. Now I will take the moment about point B. So I'm going to take moment about point B. The moment about point B is, look at the moment given by f of x. F of x is giving the moment in this direction. curl your fingers in the direction of movement, and you will notice that thumb is going out, so that movement is actually negative. So I have, and then f of x, curl your fingers in the direction of the movement. Actually, I need to show this. So check this out. Some of you may not come from the mechanical background, or it might be quite a few years before you did this. So look at my coordinate frame, x, y, and z. Are you with me? The right hand coordinate frame. Now I have two forces. One is f of x and f of y. I want to take the moment of f of x about point B. I want to take the moment of f of y about point B. Now let's look at f of x. F of x is going towards left. Do you agree with me? F of x giving a moment which is counterclockwise. Curl your fingers in the direction of the moment given by f of x. Do you agree with me that your thumb is pointing in the positive z direction? Yes. Which means the moment given by f of x is positive. Everyone understood this? Once again, right hand coordinate system, x, y, z. So right hand coordinate system is x, y, z. So for that, I have shown the coordinate system on top. That is the exact same coordinate system that I have used when I set the problem up. Now there are two forces, f of x and f of y. Movement could be clockwise or counterclockwise. What is our convention? If we curl our fingers in the direction of rotation or in the direction of movement, and if our thumb is pointing towards the positive axis, that rotation or that movement is positive. Everyone understood this? Now I want you to look at the f of y force. Can you see that force is going towards left? When that f of y is turning counterclockwise about the point B. Oh, sorry, f of x. F of x is going towards left. So it's turning counterclockwise. So curl your fingers in the direction of rotation of f of y. Thumb is coming out. Can you see that thumb is aligned with z? So the moment given by f of x is positive. Everyone understood this? Okay. Now look at f of y. When you look at f of y is going down. The moment given by f of y is like this. Curl your fingers in the direction of movement. Can you see that the thumb is going towards the board, opposite of the z-axis? Which means the moment given by f of y is negative. Everyone understood this? No? Yes? No? Once again, f of y, moment is like this. And that is actually very important because when we solve for forces, same convention will be used. Curl your fingers in the direction of the movement. Thumb is going towards negative z, which means that moment is negative. Yeah.
Why is it opposite from where the torque is going towards?
Because, so it doesn't matter. At conventions are for convenience. The most important point here is I started with the right hand coordinate system and I'm solving the entire problem in the right hand coordinate system. As long as my coordinate systems are consistent, to be honest with you, at this point, I do not know if the directions of tau 1 and tau 2 that I have assumed are correct or not. If the directions that I have assumed are incorrect, then in the answer, the sign will be negative. So now here, so summation, so f of x multiplied by L2 sine theta 1 plus theta 2, and this moment is positive. And then what we have is f of y minus f of y L2 cosine theta 1 plus theta 2 is negative. And don't forget, we have our tau 2. Curl your fingers in the direction of tau 2. And can you see that my tau 2 is positive? Do you agree with me? Okay, tau 2 is equal to this big 0. Okay. Now I hope everyone understood this equation. Okay. So I'm going to write this equation down slightly differently. I would say tau 2 is equal to minus f of x L2 sine theta 1 plus theta 2 plus Fy L2 cosine theta 1 plus theta 2. Now, the story does not end there. Now, the important part is, remember, we are drawing free body diagram. So we have freed the bodies. As soon as we free the bodies, the reaction forces or virtual forces come in the picture, which means you see those Bx and By that are acting on the joint. So you are going to have some other forces, which is Bx and By acting like this. So you are going to have Bx like this, and then you are going to have By, which is like this. You are going to have Bx and By would be acting like this.
So
Oh, sorry, By direction would be opposite. By would be acting like this. And what you are going to have is, since we have freed the joint, then what's going to happen is you are going to have a reaction torque over here, just tau 2. So you are going to have a reaction torque over here. Now, since we have freed the joint from here, again, you are going to have forces, and I'm going to assume these forces to be like this, Ax, and you would have Ay, and you are going to have the reaction forces Ax and Ay over here. Now, what does that mean? It means when everything gets combined, so you're going to have tau 1 here. Then the reaction forces kind of cancel each other out. So now what we are going to do is we are going to follow the same logic, but we know from our equation By is equal to Fy. So I can write this expression as Fy. We know from our expression Bx is equal to Fx. So this is going to be Fx. And I'm going to write down summation of forces in x direction is equal to 0. And that means 0 is equal to Ax plus Ax minus f of x. Then summation of forces in the y direction is equal to 0. Then what that means is Ay plus minus Fy. So this gives me Ax is equal to Fx, Ay is equal to Fy. And now the most important part, I need to take the summation of moments about A is equal to 0. So I need to find out the moments about A is equal to 0. So this is point A. This distance is L1. So what I have here is I have this distance. This is theta 1. So this is L1 cosine theta 1. And this distance is L1 sine theta 1. Okay, same logic. So summation of moment about A is equal to 0. So first and foremost, again, let me draw the coordinate system. X, Y, and Z. We are taking moments about A. I want you to look at f of y that is going down. Curl your fingers in the direction of the movement. Your thumb is going towards the board. So fy times L1 cosine theta 1 is negative. Fy times L1 cosine theta 1 is negative. Are you with me so far? Fy is going down. Curl your finger. We are taking the moment about A. So it's going towards clockwise direction. Thumb is going towards board. So we have Fy L1 cosine theta 1. And now what we have, the other guy is Fx, which is nothing but Bx. Curl your fingers. There's going to be Bx L1 sine theta 1. Because if you look at the horizontal force Bx, look at the direction in which it's giving the moment. Thumb is pointing towards U, which is in the positive Z direction. So it is positive. And then you have two torques, tau 1 and tau 2. So now if you look at those torques, tau 1 and tau 2, so you would see tau 1, curl your fingers in the direction of tau 1. Tau 1 is positive. And tau 2, curl your fingers in the direction of tau 2. Tau 2 is going to be positive. Tau 2 is going to be negative. Minus tau 2. Yeah. Which tau 2, this tau 2 expression. So fx and then vertical distance sine theta 1 theta 2, and then I have fy. No, fy cosine theta 1 theta 2. Vertical distance. No, this is correct. So this becomes 0. Now here what I want to do is, so this is actually fx. I need to write dx. This is fx. This is fx. Now what I want to do is, I want to find out the answer to this question is what is the value of tau 1 and tau 2 given the values of fx and fy. So the problem that I want to solve is what is the value of tau 1 and tau 2 given the value of fx and fy. Now I want you to understand this problem very, very carefully. This is equation 1. This is equation 2. In equation 1, I have tau 1 and tau 2. In equation 2, I just have tau 2. Are you with me? So what I'm going to do is, I'm going to substitute tau 2 from equation 1 in equation 2. So I will have minus f of y L1 cosine theta 1 plus f of x sine theta 1 plus tau 1, and then I'm going to substitute this equation 1, which is what? Fx L1. Oh, L1. Yeah, L1. I miss L1, right? L1. Okay, L1. This would become tau 2 will become minus f of x L2 sine theta 1 plus theta 2 plus f of y L2 cosine theta 1 plus theta 2. This step is very important. and I want everyone to just make sure that my math is working out correct. Because if signs are flipped, the answer will not come right. So this has become minus f of y L1 cosine theta 1 plus f of x L1 sine theta 1 plus tau 1 plus f of x L2 sine theta 1 plus theta 2 minus f of y L2 cosine theta 1 plus theta 2. Are you with me? Now what I'm gonna do is, I'm gonna take tau 1 on one side and all the mathematics on the other side. So I would just have tau 1 on one side, which means all the signs would be reversed. But I'm gonna take one more step. I'm going to collect f of x's together. I'm gonna collect f of x, and then I'm gonna collect f of y and f of y. So I'm taking two steps at the same time. I'm going to collect the terms and flip the signs. So this would be f of L1 sine theta 1 plus L2 sine theta 1 plus theta 2 minus f of x. Are you with me so far? I'm going to flip the sign again. Plus, I'm going to have L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2 and f of y. Are you with me? Okay. Now I will write the expression for tau 2, and now see, magic would happen. Okay, so everyone pay attention on the board. I will give you time to copy down. What? Where, Sanira? It's quite possible. Minus. No, minus. I flipped the signs. I took tau 1 on one side, so the signs would be negative, no? Yeah. So I will have to add minus here. Okay, good. Okay, tau 2. I already have an expression for tau 2, and I'm gonna rewrite this tau 2 expression slightly differently. So please pay attention. This is gonna be L2 sine. I don't know if you can track where I'm going with this, but can you guess what's happening here? F of x plus, then you would have L2 cosine theta 1 plus theta 2 Fy. Now, what this means is I can write these two expressions in a matrix vector form. Tau 1, tau 2 is equal to minus L1 sine theta 1 plus L2 sine theta 1 plus theta 2. L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2 minus L2 sine theta 1 plus theta 2. L2 cosine theta 1 plus theta 2. Are you with me so far? F of x, f of y.
Can anyone tell me what that matrix is?
Transpose of Jacobian.
It's the transpose of the Jacobian.
So if you look at the Jacobian that we have derived, where did we derive the Jacobian? We derived Jacobian here. This is the transpose of the Jacobian.
Now, what does it mean? It means if you find the Jacobian, you can not only relate the joint velocities to the end effector velocities, you can find out, you can relate the joint torques with respect to the external load. So imagine if you have a robot, that robot is going very slowly. If you want to find out what are the joint torques, you just have to find the Jacobian, and then it will give you the values of instantaneous torques as the robot is going from point A to point B. Another example, you understand this is a matrix, and it is quite possible that because of the values of theta 1 and theta 2, that this matrix could become singular. What do we mean by matrix becoming singular? Which means basically you won't be able to find out the values of torques for the given values of forces. So Jacobian talks about the singularity. Jacobian gives you the relationship between the joint velocities and the end effector velocities. And why does this happen? All this magic comes because of virtual work. And virtual work is an extremely important topic, often ignored in statics or mechanics of material. So what I want to tell you is, let me give you an example. What is work? Work is force multiplied by displacement. Do you agree with me? So which is nothing but F multiplied by delta X. Work is also given as torque multiplied by the angular displacement. Multiplied by angular displacement, which is T times delta theta. Now understand, energy can neither be created nor be destroyed. So for example, if you have this robot arm, and what you want to do is, you want to move that end effector from point A to point B, there will be some work done. There will be Fx multiplied by the displacement under that force delta X. There will be Fy multiplied by the displacement under that force delta Y. So what it means is the total work that is needed to displace the end effector has to come from the work done by the motors. Energy can neither be created nor be destroyed. So if you want to move an end effector, then you need to supply some work, some energy. Work and energy are interchangeable. So energy needs to be dissipated, or energy needs to be supplied by the motor. So energy supplied by the motor is equal to the energy needed for the work, the displacement, for the end effector displacement. So I can write this something like this: is F delta X is equal to tau delta theta. Now please understand, delta X we did over here. This gave me equation, check this out. Delta X is equal to Jacobian delta theta, because I have the derivative with respect to time on the left hand side, I have the derivative with respect to time on the right hand side. So I have the instantaneous changes in the delta X is equal to the Jacobian multiplied by the instantaneous changes in the angle. Everyone understood this? Think about it like delta t. So you have dpx by dt is equal to a matrix multiplied by d theta 1 by dt. So dt goes, and what you have is delta x is equal to Jacobian is equal to delta theta, which simply means that you are looking at the same time interval.
So I have this relationships. Delta x is equal to Jacobian times delta theta. I would use this relationship and put it over here. Delta x is equal to Jacobian times delta theta is equal to tau delta theta. Now, Jacobian is a matrix. So this thing goes. So what I want to do is here, actually this, just to make sure that this equation is correct, I need to have the transpose because it's a vector. So this is the, so you have something like fx, fy multiplied by delta x, delta y is equal to tau 1, tau 2 multiplied by theta 1, theta 2. So this is the expression. That's why you need to have the transpose. So what you have here is you have F transpose, T transpose. Now what I need to do is I can cancel out theta over here, and I have the expression F transpose Jacobian is equal to tau transpose. Now what I'm gonna do is I don't want tau transpose, I just want tau. So I'm gonna take transpose here and I'm gonna take transpose here. So what I have is I have this matrix equality AB transpose is equal to B transpose A transpose, which means this is going to become J transpose F transpose transpose is equal to transpose of a transpose is tau, which means this expression is going to become J transpose F is equal to tau, and that is what we have. We'll stop here.